For decades, we've scanned the heavens for killer asteroids. We've built watch lists, practiced deflection missions, and told ourselves we were ready. Turns out, we were looking for the wrong thing. Just last week, a ghost appeared in our telescopes, a massive, long-period comet thrown at us from the darkest edges of our solar system. Its path is a statistical nightmare, a direct collision course with Earth, impact in 365 days. Our asteroid defense plans? Useless. We have 1 year to try something so audacious it's never been attempted before. We've known about the threat from space for as long as we've been looking up. The planet has the scars to prove it. From the Tunguska event that flattened a forest the size of a city, to the Chicxulub impactor that ended the age of dinosaurs. That's the kind of terrifying power we're trying to avoid. Because of this, we got serious about planetary defense. NASA's Planetary Defense Coordination Office, created in 2016, tracks near-Earth objects and runs simulations for the worst-case scenarios. This work led to one of the coolest achievements in modern science, the Double Asteroid Redirection Test, or DART. In 2022, NASA slammed a spacecraft into the little asteroid Dimorphos, proving for the first time that we can actually change the course of a celestial body. The impact shifted the asteroid's orbit by a full 32 minutes, a massive success that blew past the mission's minimum requirements. It was a watershed moment, a declaration that we are no longer just passive victims of cosmic chance. We finally have a shield. The problem is, the thing hurtling towards us now isn't an asteroid, it's a long-period comet. And against this enemy, our brand new shield might as well be made of paper. So, what's the difference? An asteroid is a rock. It's predictable. It follows a stable orbit, mostly on the same level as the planets. We can track them decades in advance, and, as DART showed, we can give them a shove. A comet is a different beast entirely. They're primordial snowballs of ice, dust, and rock from the Oort cloud, a huge, chaotic sphere of junk at the extreme edge of our solar system. They can come at us from any direction, at terrifying speeds. A typical asteroid might hit us at around 15 kilometers per second. A long-period comet can slam into us at over 50 kilometers per second. That's more than 3 times faster. This speed difference is everything. The energy of an impact is mass times velocity squared, so a comet the same size as an asteroid can hit with nearly 10 times the destructive force. And this comet, which astronomers have named Erebus after the Greek god of darkness, is not the same size. It's a monster, estimated to be over 10 kilometers in diameter. An object like this, hitting at that speed, wouldn't just be an extinction-level event, it would be a sterilization event, unleashing more than 40 times the energy of the Dino Killer, potentially boiling the oceans and scouring the planet of all life. This is where all our plans fall apart. So, what on earth can we do? With the 1-year clock ticking, leaders and scientists scrambled in emergency sessions. The first, most obvious idea was to repeat the DART mission, but bigger, much bigger. The plan? Build a fleet of heavy-duty kinetic impactors and launch them straight at Comet Erebus. It sounds good, right? A kinetic impactor is our only tested method. You hit the thing, transfer your momentum, and nudge it off course. Simple. But against Erebus, the math just doesn't work. DART was a 600-kilogram spacecraft hitting a 160-meter asteroid. Erebus is over 10 kilometers wide and ridiculously massive. Launching every single heavy-lift rocket on Earth, packed with the densest stuff we can find, would be like shooting a BB gun at a freight train. We might chip the paint, but we wouldn't slow it down. On top of that, comets aren't solid rocks. Many are just rubble piles, loose collections of ice and rock barely holding themselves together. A big impactor might not push the comet at all. It could just bury itself in the soft surface. Or worse, shatter the comet into several large, continent-killing pieces. Suddenly, instead of one bullet heading for Earth, we'd be facing a shotgun blast. When the impactor plan was tossed out, the conversation turned to the most powerful tool we've ever invented: the nuclear option. This has been the go-to Hollywood solution for decades and a serious proposal in defense circles. The idea isn't to blow the comet to kingdom come. That would just create the same shotgun problem, but with the added bonus of radioactive fallout raining down on us. The smarter plan is a nuclear standoff detonation. You don't hit the comet, you detonate a massive nuke a few hundred meters from its surface. The flash of X-rays and heat would vaporize the surface on one side. This acts like a giant rocket engine, creating a powerful jet of gas and rock that pushes the comet in the other direction, hopefully just enough for it to miss Earth. But even this, our most powerful play, is a huge gamble. The standoff distance has to be perfect. Too close and you risk breaking the comet apart. too far and the push is too weak. And comets are notoriously flaky. As they get closer to the sun, their ice turns to gas, creating jets that can change their spin and path in ways we can't predict. A nuclear blast could trigger a catastrophic outgassing event, making the whole thing break apart. We'd be betting the entire planet on a single, high-stakes roll of the dice. So, we were stuck. Plan A was too weak and Plan B was way too risky. The freight train was coming and we were standing on the tracks with nowhere to go. We needed a new plan, something that had only ever existed in theory. With all conventional options off the table, humanity turned to a desperate, wild plan born from the bleeding edge of AI, robotics, and astrophysics. Codename Project Swarm. The idea was radical. Instead of one big, clumsy push, Project Swarm would dismantle the threat piece by piece, using thousands of small, smart, autonomous probes. It wasn't a hammer, it was an army of ants working together to move something thousands of times their size. The plan was built on the incredible advances in AI-driven drone swarms, which had already shown they could coordinate on complex tasks without a human pulling the strings. Project Swarm would be made of 4 different kinds of probes, each with a special job, all coordinated by a decentralized AI network that let them act as one. First, you have the Scouts. Launched ahead of everyone else, these small, speedy probes would be the first to arrive. Their only job? Gather data. Armed with advanced sensors and radar, they would swarm around Comet Erebus, creating a perfect meter-by-meter map of its surface. They'd analyze its makeup, find its weak spots, map out the volatile ice, and track those unpredictable gas jets. This fire hose of real-time data was the foundation for the whole mission. Next up, the drillers. These were the workhorses. Heavier and tougher, the drillers would use the Scouts' data to land on the most stable spots they could find. Using lasers and ultrasonic drills, they would bore deep into the comet's core. Their goal wasn't to destroy, but to prepare. They were the sappers, setting the stage for the next phase. That next phase would be handled by the pushers. These probes were basically compact, powerful engines. The drillers would embed them deep inside the comet at thousands of strategic points. They weren't bombs. Think of them as tiny, steerable rocket motors. On command from the swarm's AI, these pushers would fire in perfectly timed, coordinated sequences. It wouldn't be one big explosion, but a symphony of thousands of small controlled pushes over weeks and months. Some pushes would counter the comet's spin, others would gently nudge its trajectory. Together, they would slowly and carefully steer the massive object onto a new, safer path, avoiding the risk of breaking it apart. Finally, there are the shepherds. These probes were a mix of kinetic impactors and gravity tractors. It was a given that the mission would make a mess. Small chunks would break off. The shepherd's job was to be cosmic sheepdogs. For smaller bits of debris, they would use their own gravity to gently pull them into a harmless orbit. For bigger, more dangerous pieces, a shepherd could sacrifice itself, delivering a small, precise hit to knock the rogue chunk away from Earth. The brain running this impossibly complex dance wasn't a single computer. It was a distributed intelligence woven into the swarm itself. Each probe had its own processor, but they were all linked, sharing data and recalculating the plan on the fly. The system was designed to be adaptive. If a solar flare knocked out communications with Earth, the swarm could carry on by itself. If a driller was taken out by a sudden gas jet, the AI would instantly retask other probes to pick up the slack. It was a self-healing, self-optimizing system. Humanity's ingenuity in a cloud of intelligent machines. The theory behind Project Swarm was brilliant, but pulling it off was a whole other story. We had less than a year to build and launch an unprecedented armada into deep space. The entire planet's industry spun into high gear. Factories were retooled and space agencies pooled their resources, launching rockets almost daily, sending thousands of probes on their way. The months-long journey to the comet was agonizingly quiet, but once the first scouts arrived, we saw how terrifying the challenge really was. Comet Erebus was even more volatile than we'd feared. The data showed a chaotic, unstable body that was actively tearing itself apart as it got closer to the sun. The surface was a minefield of erupting geysers and shifting icy ground. The first Rillers began their descent. The swarm AI guided them to spots the scouts had marked as stable, but stability was a relative term. In the first hour, dozens of probes were lost, swallowed by surface collapses or flung into space by violent jets of gas. Each loss was a blow. But the swarm adapted. The AI instantly recalculated landing paths, analyzed the failures, and updated the approach for the remaining probes. It was brutal trial and error, playing out millions of kilometers from home. The first major crisis hit 3 months before impact. A deep, miles-long crack started spreading across the comet, threatening to break off a chunk the size of a small country. If it broke free, Earth would face 2 devastating impacts, not one. The mission had to change, right now. Back on Earth, human controllers could only watch. The communication lag was too long to do anything. The decision fell entirely to the swarm AI, and it did something incredible. The AI reprioritized everything. It diverted hundreds of pusher probes and gave them a new job. They began firing in a rapid, pulsing rhythm along the edges of the crack. They weren't trying to move the comet anymore, they were performing cosmic surgery. The synchronized bursts acted like stitches, pushing the 2 sides of the fissure back together, stopping the fracture. It was a delicate, high-stakes gamble that lasted for 48 agonizing hours, but it worked. The fragment was secured. With that crisis averted, the main mission resumed. The slow, methodical push began. On Earth, all anyone could do was watch the telemetry data, seeing the comet's projected path shift by microscopic amounts each day. Every tiny change was a victory. The final push was set for the last possible week. Every remaining pusher would fire in one last massive coordinated burn. But the comet had one last trick up its sleeve. As it neared Earth, a huge plume of dust and gas erupted from its surface, wrapping it in a dense cloud. This debris blinded the swarm's senses and threatened to destroy the remaining probes. The shepherds, the unsung heroes of the mission, flew into action. They formed a protective screen in front of the swarm, using their own bodies to absorb the worst of the debris, sacrificing themselves to clear a path. Through that path, the final command was given. Thousands of engines fired as one, and deep in the cold of space, the great comet, the harbinger of darkness, finally began to turn away. In the end, Comet Erebus flew past Earth. It was close enough to be a brilliant temporary star in the night sky, a beautiful and terrifying reminder of what we almost lost. The world watched and let out a collective sigh of relief. Project Swarm had worked. Humanity faced down an existential threat. And through ingenuity, collaboration, and a whole lot of desperation, we survived. Now, this story was a work of fiction, but the threat is very real. We live in a cosmic shooting gallery. The good news is the work to protect our planet isn't science fiction. NASA's DART mission was a monumental first step, proving that planetary defense isn't just possible, it's practical. Upcoming missions like the NEO Surveyor are essential to help us find these threats long before they find us, because time is the one thing no brilliant plan can buy. The success of DART shows that with enough warning, we can protect ourselves. Supporting planetary defense isn't a luxury, it's an insurance policy for the future of our species. The universe might be in a different place, but we have the brains and the technology to be the guardians of our own world. The question is no longer if we can stop a killer comet, but how. The fictional Project Swarm is just one idea. There are others, from gravity tractors to lasers. So what do you think? What's the most promising way to defend Earth? Let us know in the comments.